Let's try to understand how a Voltaic cell works. Voltaic cell is named after an Italian physicist and chemist by name Alessandro Volta. He was the inventor of the electrical battery in early 19th century. So let's take a look at the structure of the Voltaic cell. Well, you have two metals, zinc and copper here, and they're connected externally by a conductor. It could be a metallic wire, say copper wire, and then you have a high resistance voltmeter to measure the voltage, and then we have a salt bridge to complete the circuit, and then we have these two metals are basically immersed in respective salt solution. So zinc metal, it could be immersed in aqueous zinc sulfate or zinc chloride, and this copper electrode could be immersed in a corresponding salt solution, let's say copper to sulfate or copper to chloride. So the big picture about Voltaic cell is a Voltaic cell is basically used. So here we are using a redox reaction to produce electricity. So that is the net change that happens in a Voltaic cell. We are converting chemical energy to electrical energy, and this happens naturally. So if you take two metals differing in reactivity, you connect them through an external circuit using a conductor, right? So there is a natural flow of electrons. So this reaction happens naturally. That's why we call this as a spontaneous redox reaction. So this redox reaction is spontaneous. It happens naturally. Now let's try to understand what exactly is happening here. So this is our zinc half cell and this is our copper half cell. So let's say what's happening in the zinc half cell. So zinc is more reactive than copper because zinc is higher up in the reactivity series. So since zinc is more reactive, it loses electrons. So this is the source of electrons. That's why it has a negative charge on this metal plate or electrode. So zinc being more reactive loses electrons to copper. So the electrons are traveling from zinc all the way to copper. So zinc is the source of electrons. It's losing electrons, has a negative charge. Copper end is electron deficient, so this electrode is positive. So let's write separate equations. What is happening at the negative electrode, which is zinc here in this case. So negative electrode is zinc here, and sometimes they also call this as anode in a Voltaic cell. Not a good term, but let's say what's happening at negative electrode. So we say zinc is losing electrons. So zinc solid, the zinc solid atoms in this electrode, they're losing electrons to form zinc 2 plus ions. So usually zinc forms zinc 2 plus ions. So whatever the Zn2 plus ions that are formed, they basically go into this solution here, the zinc salt solution. And these electrons that are lost, they travel through this external circuit and go to the copper electrode. So here zinc is losing electrons, so we can call this process as oxidation. So at the negative electrode, it's oxidation. And we're saying zinc atoms are being converted to zinc 2 plus ions. They're going into the solution. So this electrode is losing mass. So there's mass loss at this electrode because these zinc atoms are continuously losing electrons and going into this solution. So there is a mass loss. The mass of this zinc electrode will decrease. So now let's see what is happening at the copper electrode on this side. So this is positive electron deficient. So at the positive electrode in a Voltaic cell, sometimes we call this as cathode. So the positive electrode is copper here, also known as cathode in a Voltaic cell. So what exactly happens at the positive electrode? Well, we said the electrons are traveling from the zinc electrode or the negative electrode, and here you have copper 2 plus ions on the surface of this copper electrode. You have copper 2 plus ions. So the copper 2 plus ions that are present on this electrode, they gain electrons. The electrons that are lost by zinc, they're gained by the copper 2 plus ions to form solid copper metal. So this process is basically reduction because electrons are being gained. So this process is reduction. So this process happens continuously. Copper 2 plus ions are continuously being reduced and getting deposited as copper metal on this copper electrode. So the mass of this cathode will increases. Well, so mass increases here. That's what I can say, because the copper metal is getting deposited continuously, right? So there is a net transfer of electrons from the more reactive metal zinc to the less reactive metal copper. And you can design a voltaic cell with any two metals differing in reactivity. Now let's try to understand what is the function of this salt bridge here, right? So we said a salt bridge basically completes the circuit. So this is the salt bridge. So usually we can use a glass tube or even just a filter paper that is immersed in aqueous potassium nitrate. This is usually used, and the chemicals in the salt bridge, they should not react with the electrodes or with the solutions here. So that's very important. So since potassium nitrate doesn't react with the electrodes here or the solution, so it's a safe bet. So this is what happens in a salt bridge. Let's draw a simple diagram to understand how it works. So this is my, let's say that's my zinc half cell. This is my copper half cell, and they're connected by this salt bridge. This is my salt bridge, and we are saying in this salt bridge, so we have potassium nitrate here, right? So here in this zinc half cell, there is an excess of zinc 2 plus ions. So there is an excess of zinc 2 plus ions because the zinc atoms are continuously oxidized to zinc 2 plus. Whereas in this copper half cell, so here I can say in this half cell there is a deficiency of positive charge, or copper 2 plus ions deficiency. So this is not good. If the positive charge is greater here, if it is less here, and eventually if this positive charge drops to 0, there will not be an electric current. That's not good. So your voltaic cell will be of no use if it cannot produce electricity. So how does this salt bridge maintain a constant positive charge? So let's take a look at this. So since there is excess of zinc 2 plus ions, so this half cell gets rid of some of this excess positive charge in this manner. So let's say a zinc 2 plus ion migrates from this half cell to the salt bridge. So you have a Zn2 plus or zinc 2 plus ion transferred from this half cell to the salt bridge, and that's replaced by two NO3 minus ions, NO3 minus and NO3 minus. So some of the excess positive charge is lost to the salt bridge, and that's replaced by NO3 minus ions. So to keep the charge constant during the transfer, so for every double positive zinc 2 plus ion moving into the salt bridge, there are two uni-negative nitrate ions entering the zinc half cell from the salt bridge, right? That's how some of the positive charge is got rid of. And something similar happens here. See, here we have a deficiency of positive charge. So we need to build up some positive charge here. So what happens is, well, there is also some sulfate ions here. So here SO4 2 minus. So let's say there is SO4 2 minus excess because it's copper 2 sulfate solution. And our goal is to build up positive charge because there's a deficiency of positive charge in this half cell. So what happens is a sulfate ion migrates here into this salt bridge. So there is a sulfate ion migrating from the copper half cell to the salt bridge, and to build up that positive charge, so what happens is that's replaced by two K plus ions, K plus and K plus. So for every single sulfate ion that enters from the half cell to the salt bridge, there is two positively charged potassium ions taking its place in the half cell. So as a result, some of the copper 2 plus deficiency is replaced by that positive charge from the salt bridge. So as a result, the excess of zinc 2 plus is removed here by the transfer of Zn2 plus to the salt bridge, and the deficiency of copper 2 plus ions is compensated by the transfer of K plus ions from the salt bridge. So the salt bridge, the function of salt bridge is usually to maintain electrical neutrality. So a salt bridge maintains electrical neutrality. So that's what it does, so that the electric current in the voltaic cell doesn't drop to zero. So that is the function of a salt bridge. So that's how a voltaic cell works.